Okay. Okay. So this paper is called Why Instant-Runoff Voting is So Resilient to Coalitional Manipulation, Phase Transitions in the Perturbed Culture. And it was presented this year at AMAS. So the paper deals with 3 voting rules. The first one is plurality, where you elect the candidate with the most top votes. So here, for example, we have a group of 36 voters who prefer candidate C1 to C3, C3 to C2, and C2 to C4. So these persons vote in favor of candidate C1. And similarly, we have 3 other groups of voters who respectively vote for C2, C3, and C4. So on the right, we can plot the scores of each candidate, and of course, candidate C1 is the winner. However, the people from the 2 last groups can realize that if they strategically put C2 at the top of their ballot, then C2 is going to win. And since these persons prefer C2 to C1, they are happy to do so. So the situation is vulnerable to strategic voting. So that is what we call coalitional manipulation. The second voting rule of the paper is the 2-round system, where you keep the 2 candidates with the highest scores and they advance to a final runoff. So here, I will take the same example. C1 and C2 are selected for the final runoff. The votes of the 2 last groups of voters are going to transfer to candidate C2. And finally, C2 is going to be the winner. However, let us come back to the original situation. People from the first and the last group may realize that if they put C3 on top of their ballots, then C3 is going to be the winner. And all these voters prefer C3 to C2, so they have an incentive to perform that manipulation. So here again, the situation is manipulable by coalition. And the third voting rule of the paper is instant runoff voting, which is also known as ranked choice voting in the US, alternative votes in the UK. And in these voting rules, you eliminate the candidates one by one recursively. So here in our example, C4 has the lowest score, so C4 is going to be eliminated. The votes are transferred to candidate C3, which makes this candidate stronger than C2, then C2 is eliminated. And the votes are transferred to candidate C3, and C3 is going to be the winner. And in this situation, you will have to believe me for a few minutes. In fact, it's not subject to strategic voting. So no coalition in favor of an adversary of C3 would be able to change the results in a manner that is profitable to them. So in order to compare the different voting rules, what you can do is to try to estimate the frequency of this vulnerability to coalitional manipulation. So that's what we did in a previous article with a data set of preferences that is called the Netflix data set, which is in some sense a subset of the data set of the Netflix price that you may know. So what we do is that on the x-axis, we put many voting rules, so the 3 that I presented and many others. On the y-axis, you draw the CM rate, which is the proportion of voting profiles, of voting situations that are vulnerable to strategic voting, so that are coalitionally manipulable. And so this is empirical data. This is empirical observation. We see that, in fact, I of H is much less vulnerable to coalitional manipulation than the other voting rules. But so far, it was difficult to understand why it is so. We just see it in the simulation, and it's not clear why IAV has good properties. So to try to explain this, what we do in this paper is that we use a very simplified time model of preferences for the population, which is called the Perturbed Culture. And in this model, so we have a number n of voters, n candidates, and a concentration parameter theta that will control whether the preferences of the voters are concentrated, correlated. And what we do simply is that for each voter independently, with probability theta, this voter will have a fixed ranking of preference. So she will prefer C1, then C2, then C3, and so on. And with probability 1 minus theta, she will have a uniform random ranking. So in the particular case where theta is equal to 1, all the voters will agree because they will all have the same preference ranking. And in the particular case where theta is equal to 0, then it amounts to what is classically called in voting theory the impartial culture, which is simply to take the preference of everybody uniformly at random. So in this very simplified framework, we can study the CM rate of plurality. So let's go on the x-axis. We will put the concentration parameter theta. So on the left, it's 0, so it's a high level of disorder, and on the right, it's 1, so a very high level of order in the population. And on the y-axis, we put once again the CM rate, so the probability that a given a voting profile is susceptible to strategic voting. So when there is only one voter, of course, very easy. It's not manipulable. So the CM rate is equal to 0, whatever the concentration parameter is. And when you increase the number of voters, so this curve takes on a sigmoidal shape and steepens and steepens. And in fact, we show theoretically that when n tends to infinity, in fact, this curve tends to a step function, which means that there is a critical value of the concentration parameter theta. And below this concentration parameter, so when the population is very disordered, when there is a lot of dissensus in the population, in fact, it tends to be manipulable with probability 1 when n tends to infinity. And when the population is more organized, more in agreement than theta c, then for a large electorate, in fact, the probability that it's vulnerable to strategic voting tends to 0. And we show in the paper that the value of the critical parameter is m minus 2 over 3m minus 2. So it depends on the number of candidates. So we can do essentially the same for the two-round system. So here we go again, a bit more quickly. So here again, the curve takes on a sigmoidal shape, it steepens, and there's also a critical value of the parameter. It tends to a step function. And here the critical value is equal to m minus 3 over 5m minus 3, which means that, so it's lower than for plurality. So it means that when the concentration of the preferences of the population increase, the two-round system becomes resilient to strategic voting more quickly than plurality. So it is in some sense better than plurality. And now for the third voting rule, so instant runoff voting. So here we go again. So here, in some sense, it's the same, but it's a bit different because here the critical value of the parameter is equal to 0. So this means that in this very simplified model of the Perturbed culture, as soon as you have the slightest concentration of the preferences, then IRV will become immune to strategic voting in the limit of large electorates. So why it is so, in fact, is due to the notion of Super Condorcet Winner. So I will try to explain this in a few relatively quickly. So let's take our initial example. So I will show you that in this example, candidate C3 is the Super Condorcet winner. So I will show you the example and then I give the definition. So here, when you have the 4 candidates of the profile, candidate C3 has more than 1/4 of the votes. When you have this subset of 3 candidates with C2, C3, and C4, C3 has more than 1/3 of the votes. It's also the case when you have the subset with C1, C3, and C4. Also the case when you have C1, C2, and C3. And for the subset of 2 candidates, so when you have C3 and C4, C3 has more than 1/2 of the votes. So in particular, it's the classical condition for a Condorcet winner. It's also the case against C2, and it's also the case instead C1. So altogether, this condition defines the Super Condorcet winner. So essentially, for any subset of K candidates that includes C3, C3 would have more than a proportion 1/k of the plurality votes. So in the Perturbed culture, as soon as theta is positive, in fact, you can show that there is a Super Condorcet winner with high probability, which in fact is relatively intuitive because the condition that we demand is not that strong. In fact, if you are in a uniform culture, in a subset with K candidates, you expect to have a fraction 1/k. So we just ask that you have more than that. So of course, we ask that it's the case for all the subsets and all the Ks, but we just ask you to be just above what is expected in a totally uniform culture. So as soon as you have the slightest bias in favor of a candidate, in fact, with high probability, this will happen. And of course, if there is a Super Condorcet winner, she will be elected by instant runoff voting. Why? Because in any round, she will have a score that will be higher than the average. So she cannot have the worst score. So she cannot be eliminated. That's easy to see. And it can be proven. It's not that difficult to prove that also it's not susceptible to strategic voting. So not only does she win, but it's also resilient to strategic voting. So that's only, so the presence of a Super Condorcet winner is only a sufficient condition to ensure that IRV resists strategic voting. But in theory, it can be the case that IRV resists strategic voting, even in cases where there is no Super Condorcet winner. So does that happen often? So to know that, we can have a look at empirical data sets. So I will take once again the Netflix data set that I mentioned earlier. So the proportion of profiles. So in this data set, IRV is immune to strategic voting in 95% of the profiles. And in fact, there is a Super Condorcet winner in 94% of the profiles. So it's a very good explaining factor of the resilience of IRV to manipulation. It does not cover all the case. There are some like knapsack edgy cases, but most of the time, in fact, it's the reason of the resilience to manipulability. And in the paper, we also deal with another data set where the correlation is even clearer. In the paper, we also show that in the theorems establishing the existence of a critical theta, in fact, all the convergences are exponentially fast. So for each value of theta, except the critical value, so the probability tends to 1 or tends to 0. And this convergence is exponentially fast, which means that the results that we have for large electorates quickly become relevant even for relatively small value of n, in fact. So you saw that when I showed the animations, I stopped at n equal to 2056, and already it's relatively close to the step function. And also in the paper, we also studied the critical case, which is very difficult from a theoretical point of view. It's often like that in phase transitions. So we studied a critical case by simulation. And I think that's it. Thank you very much. Just want to say one last thing, that for this presentation, I used a Python package that is called manim, which has been made by the guy who has the YouTube channel 3 Blue 1 Brown, which is an amazing YouTube channel about math. And I knew of that package thanks to the reading group Tools, Tips, and Tricks of the links, because Leonardo, who is not here today, I think, showed us what manim is, and okay, thanks to that, thanks to the links.
So this is a very fun topic, very timely. The US keep changing the way we write and vote. So, but I'm wondering, how does this fit into a bigger long-term picture? Does Links have a topic on election integrity, or is it just a fun thing you embarked on, or?
Essentially, let's say that it's part of history of the links, a bit, yeah. So at the beginning, I worked with Ludovic Noiry and another former member of the links, Fabien Mathieu, about voting rules, including some applications to networks, like voting about choosing path, choosing routes in a network. And you see life.